Starting equations for conic sections in polar form. So we got r equals k over a plus b cosine theta and r equals k over a plus b sine theta. So the two variables that really determine the shape and type of the graph are a and b. So the relationship between a and b is what will determine whether or not your graph is a hyperbola, parabola, circle, ellipse, while k really acts as a scalar to the base behavior, but changing k won't change whether or not the graph is a circle, ellipse, hyperbola, etc. So then the difference between the cosine equation and the sine equation is the axis of symmetry for all of the sine equations is the y-axis, so they're symmetrical that way. And then for cosine, they are symmetrical about the x-axis. So those are really how those two are different. So other than that, like the base functions and what determines whether or not something's a parabola or hyperbola remains the same between the two.
To understand how graphs of conic sections work on a polar coordinate system, you first need to know what a conic section is. A conic section is one of these four different shapes: A, an ellipse; B, a hyperbola; C, a parabola; or D, a circle. Now look at the conic section equation, where r is equal to the quantity k over a plus b cosine theta, where a, b, and k are constants. Theta is the input, and r is the distance from the origin to the point. But how does this equation allow us to make elliptical, hyperbolic, and parabolic shapes? That all depends on the a, b, and k values. K is just a scalar for the equation. But what's more interesting is A and B. A and B determine the eccentricity, or a variable E, of the graph. In simple terms, the eccentricity of the graph is the magnitude of the constant B over A, represented by the variable E. When E is greater than 1, or when B is greater than A, then the graph forms an ellipse. When E is less than 1, or when B is less than A, well, I got my things mixed up. In simple terms, the eccentricity of the graph is the quantity B over A, the magnitude of which gives you E. When E is less than 1, then the graph forms a closed ellipse. When E is greater than 1, the graph forms an open hyperbola with two distinct sides. And when E is equal to 1, the graph forms a parabola. This is because the range of theta for either sine or cosine is between 0 and 1, meaning that the range for the denominator is mostly dependent on the relationship between A and B and how those numbers add together. The sign, positive or negative for either A or B, does not actually matter, since there will always be an angle for theta. For instance, for our cosine function, theta can be root 2, theta can be 45 degrees or 135 degrees, and give you positive or negative depending on what you chose. You will see from the tables in a few moments how the values of r scale up or down, depending on theta values compared to the eccentric values. But first, you get to see it on the graph. You can see from the graph that k is really just a scalar, and as k increases, for the cosine function, it results in a vertical stretch, and for the sine function, it results in a horizontal stretch. What's more interesting is the relationship between a and b. When the magnitude of b is less than the magnitude of a, it forms a closed ellipse. When the magnitude of b is greater than the magnitude of a, it forms a hyperbola. Good thing to note, once again, is that the signs of these don't actually matter. I can have both be negative, one be negative and one be positive, or both be positive. And the actual type of conic section the graph forms is unaffected. You can also see that if I make these equal to each other, it forms, as expected, a parabola. But even if one is very slightly larger than the other, and it appears to be a parabola, you can see if you zoom out enough that it isn't. The same applies to the a value, as it forms a closed ellipse when you zoom out enough. But what happens when one of these values is equal to 0? Well, when b is equal to 0, there is no theta input. It merely becomes a relationship between k over a is equal to r squared. And if you remember, r squared is actually the distance from the origin to whatever point you're mentioning, which means that it is the square root of x squared plus y squared. And if you write that down, it starts to look like the equation for a circle. So the equation would end up being x squared plus y squared is equal to the quantity k over a squared, which is a constant, which is why it forms this circle. When b is equal to some value and a is equal to 0, it ends up forming this strange pattern line where in the cosine function, it results in a vertical line, and in the sine function, it results in a horizontal line. This is because once you convert it into Cartesian, it's a lot easier to see. But what ends up happening is that x ends up being set equal to a point, or if you're using the y function, sine ends up being equal to a point, which is why that the cosine function forms a vertical line, because in this case, x is equal to this value here, and y for the cosine function is also equal to that value, which is why they cross right here. And of course, you cannot have b and a equal to 0, which makes sense because then there's just no denominator. Denominator equals 0. You can't do that. Another important thing to note is that there's an interesting relationship between conic sections and Lima codes. If you look at the equation for a Lima code is actually the inverse of a conic section, or rather, a conic section is the inverse of a Lima code. You can also see that when b is equal to a, or when there is a cardioid in the Lima code, it forms a parabola. When b is greater than a, or when there is a loop, it forms a hyperbola in the conic section variant. And when b is less than a, it just forms the little lump here with no loop and a closed ellipse. This relationship will always ring true regardless of what a or b is or the signs.
One possible shape that can be made from conics is a parabola, in both sine and in cosine form. With a parabola, as theta approaches 3 pi over 2 from pi, r approaches infinity. And as theta approaches 3 pi over 2 from 0 pi, r will also approach infinity on that side. In this graph, r is undefined when theta is 3 pi over 2 because of the sine of theta is negative 1. And 2 times negative 1 plus 2 equals 0. This makes sense because the only place where this graph hits the y-axis is at 2 pi. If there was a value of r when theta was 3 pi over 2, then the graph would not be a parabola, it would be an ellipse. This is why b equals a in parabolas, because when sine and cosine of theta equals -1, the equation will be 1 divided by a minus b, which is the same as 1 divided by 0. In equations that are 1 divided by a, b, cosine, or sine theta, the graph is reflected over the pole, and is undefined when cosine or sine of theta equals 1. Another equation that can be made from conics is hyperbolas, and once again, both sine and cosine form. Sine equation has an asymptote at the line theta equals pi over 3. As theta approaches 3 pi divided by 4 from pi, the sine of pi is closer to negative 0.5. And since 1 divided by 1 plus 2 times negative 0.5 equals 1 divided by 0, there is an asymptote there. Then there's a second asymptote where theta equals 11 pi divided by 6, because once again sine theta is approaching negative 0.5. So basically, from 7 pi divided by 6 theta to 11 pi divided by 6 r is negative, and the point is reflected over the pole. This is why for hyperbolas, a is always less than b, meaning that at two values of theta,
ellipses. Here's an ellipse that's made using sine of theta. The equation for it is r equals 1 divided by 2 plus sine of theta, and as you'll notice, our a value is 2 and our b value is 1, so our a value is greater than our b value, and this is different from the relationship between the a and b values in parabolas and hyperbolas. So this is going to be true for all ellipses. Our a's will always be greater than our b values in this form, and this is because since our a's are greater than our b's and the range of the sine function is -1 to 1, that means that we will never be able to get a value of, we'll never be able to put something in for theta where b times sine of theta is equal to the absolute value of a, which means that you'll never be able to subtract b sine theta from a and get 0, which means we'll never get k over 0, so that's why we have 0 asymptotes. And then because this ellipse is using sine of theta, we are symmetrical around over the y-axis. And then in this particular one too, the ellipse is mostly below the x-axis, and this is because between the values of theta, 0, and pi, everything we're going to get is positive, so we're adding 2 plus 1 times a positive number, which is just going to make our r value smaller because we're dividing k by a bigger number. In fact, the biggest number we're dividing k by is 3, because sine of pi over 2 is 1, 2 plus 1 is 3, so, and then on the other side, when we get to sine of 3 pi over 2, that's -1, so what we get is 1 divided by -1, which is why the lowest point is -1, so that's what really stretches it out, makes an ellipse. It's kind of just that effect happening. And then if we go over to the next slide, here's the same ellipse, except we are using the cosine of theta, and as you can see, it's really just been rotated 90 degrees around the pole. But yes, and we have our symmetry over the x-axis now, but we still have most of our ellipse to the left of the y-axis this time, so, and then our highest x value is 1/3 when theta equals 0 or 2 pi. So, and then our lowest x value is going to be -1 when theta equals pi, which makes sense because cosine of pi is -1. Circles are definitely the simplest one to explain. So the equation for this circle we see here is r equals 1 divided by 2 plus 0 sine of theta. So whenever we have our circle, our b value is going to be 0. And basically what that means is no matter what you put in for theta, b sine theta is always going to be 0. So that means the radius is going to be constant, and it's going to be equal to k over a, which in this case is 1 over 2, which is why for every single value of theta, the radius is the same exact thing, which is 0.5. And then even though we're using the sine of theta is not doing anything in this equation because it's being multiplied by 0, which is why we're symmetrical around every axis, and there's no difference between this equation and the next one, that's the wrong next equation, but there's no difference between putting sine of theta or cosine of theta in when our b value is 0. K divided by a plus b sine theta from polar form into Cartesian form. So our first step here is going to be to get rid of the fractions. So we're going to multiply both sides by a plus b cosine theta, which we then get right here. And then our next step is going to be to divide both sides by b. So we end up getting r sine of theta equals k minus ra all over b. So we know that r times sine of theta is equal to our y value, and then our r value is equal to the square root of x squared plus y squared. So this is why we end up with our final equation, y equals k plus or minus a times the square root of x squared plus y squared over b. And then this is the same thing with the cosine equations, except instead of getting y equals k plus or minus a square root of x squared plus y squared all over b, we get x equals that. So pretty simple. So then if we take a look over here, so this in red we have the cosine function equations in Cartesian form, and we have in purple the sine functions. And it's important though to notice how when it's a hyperbola like this, you only get 1/2 of the hyperbola from the Cartesian form. So that's why we have the plus or minus, because it's with hyperbolas, if you remember, it's there's a value of theta where the r's you get out are negative and reflected over the pole, or not the pole, but reflected in the opposite direction. So that's why, reflect over the pole, which is why we get the two separate parts of the hyperbola. And that's why we need to kind of use a sort of parametric equation where it's 1k plus a square root of x squared plus y over b, and one where it's k minus that. So yeah, that's the conversion to Cartesian form. Then this equation works for all of the different values that you could possibly put in for b, a, and k. So there's absolutely nothing that you could put in for this where it wouldn't work.